Our next speaker comes from our very own University of Wisconsin at the very cool IceCube project. Rick Evans is going to finish off our session on workflows and workload management.
Yep, so like you said, I'm Rick from IceCube. I'll be talking about EWMS. This is a flock of starling birds. It's pretty metaphorical, you'll find out. So EWMS, it stands for Event Workflow Management System. And we're using Condor for a very specific use case, and that's to run many, many short-lived tasks. And when I say many, I'm talking hundreds of thousands or more. And short-lived, under half an hour, roughly. It depends on resources. So what is an event? So an event is the smallest unit of work that we can subdivide our workflow into. It's a computationally independent chunk, and I'm being very vague on purpose here because it can be used, this sort of classification can be used in a bunch of different problems beyond IceCube, to astronomy or cryo-EM, OCR, etc. So as we all know, Condor is very good at aggregating distributed resources and orchestrating those workflows. But it ultimately imposes a one-to-one job task mapping, which means that what you're running should take longer, preferably much longer than it takes to start up and schedule your job, right? If we're running jobs that are 2 minutes long and we're waiting half an hour around for our jobs to get scheduled, example numbers, we're just wasting resources. We're not going to get our hundreds of thousands of jobs done, right? We're going to be waiting forever. So in contrast, these events I'm talking about have a much shorter runtime. So we're thinking, okay, how can we group these events? Do we have to group these events? Well, if we're using Condor, we have to do some type of bundling, batching, and that's what EWMS seeks to answer. So in other words, Condor is a very massive bird, but what we're dealing with is starlings, a very tiny bird. And then surprisingly, this is not AI generated. This is a flock of starlings that I'm calling condor shaped. But they're just tiny birds just like that. So EWMS, we started about 4 years ago adopting this at IceCube for the real-time alert system. Some background on IceCube, in case you don't know, it's a cubic kilometer detector in the IceCube at the South Pole. It is the premier facility for detecting astrophysical neutrinos. And when a neutrino is detected, the first thing we try to answer is, where did this come from? So unlike a traditional telescope that points in one direction and observes, or points in a direction and observes a region, right, if we're going to get specific, it detects every direction, right? And then through its detectors that light up, we're able to track about where it comes from direction, but the probability, the precision is something that is very needed when we're talking about all of deep space, right? So we want to tell these other observatories all around the world, all different types of mediums beyond neutrino observers, hey, what is this thing? Is it something we know? Is it something we don't know? We're talking discoveries, right? So in order to do this, we're constructing a sky map. And a sky map is kind of like a heat map of the night sky. So here's your Milky Way, I believe. And this is just like a world map. This is the map of the sky. And through our directional reconstruction, we're able to scan across varying granularity, hundreds of thousands of total pixels, to be able to figure out the most probabilistic direction that this neutrino came from, and then we can tell everyone else to point their telescopes in that direction. And this is how we did it before EWMS, the original solution. So we would, on our local cluster, Condor cluster, we would preempt, reserve thousands of nodes for immediate availability because we needed this thing to launch very quickly. Then we would generate our hundreds of thousands of events. We'd group those into equal size bundles. One job gets one object, which contains about 1,000 events. In our IceCube situation, these are pixels, or specifically like directions, and then a couple other numbers in there for physicists to figure out. And then we submit to Condor those N jobs, those 1,000 jobs. And then we wait for everything to finish. And eventually we get our out files, and out pops a sky map, and we're able to figure out where that direction is. So perhaps this is something similar that you're doing. If you're running short-lived jobs, I'm sure you're doing some type of bundling. And when everything works well, it's fine. So in theory, this is an okay solution, but in reality, it's not. So these are the three realities I came up with of HTC. So one, we have a heterogeneous and finite compute pool. So we don't have infinite availability. We don't have everything running on the same systems. We're not Amazon, right? Two, tasks, processes, and CPUs are going to fail for reasons that oftentimes we don't know why. Even if your software is tested, things are going to fail. That's the reality when we're dealing with thousands and hundreds of thousands. And less than ideal job availability is unavoidable. So I'm sure everyone who's ever submitted jobs to Condor has asked, why isn't my job running right now? So EWMS actually says, okay, what if you didn't have to wait for your last job to finish for all your tasks to finish? What if? So this brings me to the EWMS design, and this is more or less the complete details that I'll give, technically, not to bore you. But over here on the left, we have our user, and our user says, hey, EWMS, all the boxes. I have this thing called a workflow. Please talk to Condor and get me the resources I need. And EWMS says, all right, here are some event message queues, more on that later. And you can connect through our data broker, and those events can be shuttled on over to our execution points that are running our task pilots. You can also upload some common data to be accessed. This events, hundreds of thousands, this common data, a dozen or something like that, objects. So today, IceCube outsources Condor to EWMS for our real-time alert system. We're using Condor proper for a lot of other stuff, obviously. So just to underscore, EWMS is domain agnostic. It doesn't care that we're running physics. You could run anything you want. We're running singularity images, obtainer images. It just needs to know how to run it, not what it's running. That also makes testing really easy because we're loosely coupled. EWMS is using an external domain-specific server that kind of just wraps this up to be interacted nicely. This is the thing that does know physics. We call it SkyDriver. So in other words, SkyDriver or user is telling SkyDriver to tell EWMS to tell Condor to run our physics code. Many layers of indirection. So appropriately, I found a starling flock shaped like a penguin, though there are actually no penguins at the South Pole. There's nothing at the South Pole except for physicists. Yes, kind of. So that sounds all good. What do I need to do? How do I actually use this EWMS thing? And in short, it's all about event I/O. So from the top, EWMS is not using Condor's file transfer system for events. It's using it for other things, not events though. We're dynamically allocating our inputs, outputs, and our workforce at the same time. So instead of the file transfer system, we're using message queue passing, message passing. This is using the RabbitMQ protocol on top of HTTP. There's other protocols that we also support. This is the one we're using at IceCube. So what this means in practice is we're separating event I/O from job mechanics. which means our faster nodes out there, faster CPUs can process more tasks. Since we live in a heterogeneous environment, we want the slow machines to do, the slow machines are going to be slow, but the fast machines should process more things so we can get our job faster, we can get our workflow done, finished earlier, and we can tell the world about this thing in the sky. In other words, we actually don't care about fluctuations in job count, which is pretty good when Condor puts jobs on hold, but also that means that we can increase our number of jobs after the fact. Or we can decrease them if the thing we're looking for has decreased priority for some reason. So looking under the hood real quick, the thing that's actually running on these execution points are pilot-based, or pilots, task pilots. So that's our red cube right here. That's our task process. Our task process takes in a file from a known location. It outputs a file in a known location. Wrapped around that is our pilot. So our pilot is actually reading from a message queue. The pilot turns that event into a file that's given to the task process, outputted file, back to the pilot, and out to the output message queue 2. This is using a container right here, another container here. So apptainer in apptainer. Now, what this means is we have loosely coupled a lot of dependencies between the actual running code and the pilot code. And if anything goes wrong in this system, if any of these lines breaks for some reason, someone unplugs a server, right? Or lightning hits a building or something, that's fine, because we actually don't, EWMS does not acknowledge that an event has been received until the task is completed. All right, the execution is only taking minutes, so we're not actually losing a whole lot of work if one task finishes. This also means that the task, when it does finish, is immediately sent out, and a new event can be put through this pipeline. Technically, it's already in the queue, but the pilot can feed a new one, do the process, output, and repeat. Interacting with files makes this a bit more backward compatible to existing algorithms. EWMS tries its best not to tread on any of the exceptional features in Condor, like these, just to work with it and improve for our specific problem. So, how do you actually interact with this thing? Well, whether you're a user or a bot, it's the same interaction. We try to make this thing flexible to adopt so it can actually be used. Our submit language is not unlike Condor's. You can actually notice some similar attributes here that are used in Condor, and some that you can squint and maybe pretend like they do. Arguments, image, environment. All this is a JSON, which is submitted through REST. It's platform agnostic, of course, because it's just a JSON file or a submit object, a request object. So you can do this in any language you want. You can use in Bash just straight from the command line if you want. The validation is done on the server end using JSON schema and OpenAPI. So if you have an attribute wrongly typed, wrongly spelled, it's going to tell you immediately what it is and where it is. Using task images also allows us to test customizations, which in physics means scientific reproducibility. And we're running apptainer, like I mentioned earlier. Optionally, we can also run Docker inside. We're using Docker in our CI testing framework, which runs a very scaled down version of this. So fast forwarding to the future, we're looking at CHTC to use EWMS for things beyond our physics, and specifically protein language modeling. So we're talking millions of potential variations. Each one has a small inference task. That's good, right? That's the EWMS use case. And then additional tasks can be added in discovered regions of interest, which actually may hint at a multi-step workflow instead of the single step like we're using IceCube. Beyond this, Ian Ross also provided this use case number 2 that we can explore, which is literature processing and data mining. scanning millions of documents. Currently, what they're doing is they're batching them, right? But each individual document only runs for an order of minutes, and some documents are problemsome, which results in rebundling and resubmission. So that's exactly what we're seeing at IceCube that we have solved. It'd be fantastic to apply this to other scientific areas as well. And then something I'm interested in is exploring other workflow geometries, non-cyclic graphs. For example, filtering pipelines where the output quantity is less than input quantity. This is kind of hand-wavy, but each node would be a task type, and then each edge would be a specific event queue, and perhaps the weights correlate to priorities or event frequencies. And that's about it. I'd like to thank everyone who has helped me over the past several years on this project, NSF. Here's another Starling picture, so you all can look at that. Thank you.
Thank you, Rick. Do we have any questions?
I think we're all hungry.
Oh, we violated the fundamental rule of speaking, which is never speak before food. Well, if there are no questions, we can hit Rick up during lunch. And again, let's give him a big round of applause for Rick and everyone in the session.